Hello, this is Fahad, and we are covering Chapter 7 in Russell Smith's book for alternating current and power distribution and the voltage system. In this chapter, we will learn the following. The difference between direct and alternating current. We did talk about them a little bit, but now we'll go a little bit in depth to explain the science behind direct and alternating current. How is alternating current is produced? Difference between single-phase and three-phase power distribution system. Probably we did throw that term around, especially when we did schematic. We did look at the phase and the phase signal or sign, which looks something like that, represented by the Greek letter phi. So that is the phase, means phase. And the difference between single-phase and three-phase, we talked about that, and the basic power distribution system. By power distribution, meaning the power coming all the way from the power plant all the way to your house or your factory. So how does it work? It's really good to have an idea of how the power is distributed in case you have to work with commercial buildings. Common voltage system, they're not all the same. I know we are familiar with 240 and 120, but there are more than voltage system. We are not going to be installing or working with these kind of power systems in our jobs, but at least we have to know how does it work. The only time you might work with three-phase is when you're trying to wire a big compressor for an air conditioner. Identify some common voltage system. Just for the sake of knowledge, it's good to know what is this voltage system and how does it work. Okay, let's start. So, from chapter 2, we talked about current, and we said current is the flow of electrons. So whenever the electron flow, that's called current. I think we all agree on that. And what do we have for current? We talked about direct current, which is flow of the current in one direction. Meaning, if we look at the car battery, we have plus and minus, and the flow will go from the minus all the way to the plus, and it will keep flowing in one direction, and we will have 12 volts or whatever we have, but the voltage is always going in one direction. The alternating current has a different behavior, and we did look at it in chapter 3, and we said that the current goes back and forth, meaning if this were to be an alternating current, the current will not go from a battery, will go from a source, looking like that, and we have plus and minus going all the way through the line. And we'll talk about that. And AC is used for most utilities and most appliances, and also used in heating and cooling. So whatever we are going to plug into for our installation going to be alternating current. Okay. Basic concepts about alternating current. It's represented by a sine wave. What is a sine wave? It looks something like that. That's a sine wave. It's goes back and forth. Why is it called a sine wave? I will explain. This is basically a representation of something cyclical, something that goes in cycles, and we'll understand why. It does also change direction, going up and down. If this is a wheel turning, you can see it going up and down, and if this is my coordinate, and if the cycle, if we have a point here that keep turning, and we know that this is plus, and this is minus, and plus, and minus. If we were to imagine this is a wheel turning, and we want to represent the number that goes in that cycle, it will be going from plus to plus, all the way here, then it goes down, then down again. And if you think about it, this is what's happening here. This point correspond to this point over here. In the top here we have plus of plus, the x and y are all pluses. This is going to be the highest point, and it goes down and up again. So the sine wave is a representation of something going in circle as a representation of a wave. So that's why we have a cycle. It's a complete cycle going around, but it's starting here and goes all the way down, then goes to here. So this here is a cycle, a representation of a cycle of that wave. Frequency is the number of complete cycles in 1 second. So if this is a cycle, I'll show you in a bit better graph. If this is a cycle, so if we start from 0 and go all the way to the top and back again to 0, that's a complete cycle. So this is the linear presentation of something going in circle. I hope it makes a little bit of sense, but I'll try to talk. Here's my sine wave, the one that I talked about recently. If we look at my if this is north and south, if this is my motor going or rotor going around in circles, this is how this is represented between north and south, going up and down and up again. From this point to this point, we have completed complete cycle. So this is called a cycle. How many cycles do we complete in 1 second? That's called frequency, which is hertz frequency. So we go up, positive, this is A, which is here, goes all the way up to B, then start going down to A, the same point, then goes down again to D, then goes up again to A. So this is a good representation of what a sine wave is doing in terms of something going back and forth. And if we look at these degrees, these represent a complete cycle. So we all look at this degrees here. Oh, it's not drawing. I'll do it here. Degrees, and if this is my coordinates, here will be 0, and this is 90, and this is 270, and this here is this is 180, sorry. This is 180, and this is 270, and 0, which is 360. So this is me going around, and this other representation of this line into this graph as a cycle. There's a YouTube that explains that cycle. I hope you get to watch it. This is the link for it. You'll find the link in the PowerPoint posted with this class presentation. I'll go back to the cycle, but just to elaborate of how the power is distributed. This is my power plant here, and usually the voltage is very high, within thousands of kilovolts. That goes back to a step-down transformer, to the power lines, substation, then 50 kilovolt, which is 50,000 volts, transformer again, that goes to those little breaker and switches. It ends up in your house at 220 volts, and we said that every panel in a home has 220 volts, and commercials will take different consumption. It goes up higher than a house transformer and with different phases. So it kind of gives you an idea of what's happening when it comes to power distribution. So you need to remember that peak voltage happens at 90 degrees. I'll explain why now. And effective voltage happens at 0.707 times the highest of peak voltage. So the peak voltage would be at 9. If we multiply that by 0.7, you get the highest peak voltage. I will explain that. So remember the cycle we had? Of course, this is going to continue to go here and all the way up. This is my cycle, and this is my sine going back and forth. If we look here, this is my peak voltage. This is the highest voltage I get out of this wave. Again, if I look at the coordinates in here, this is my 90. This is the highest, so this is where I get my effective voltage. Looking at the graph, it's visibly understandable that this is my peak voltage. Okay, my lowest voltage is going to be here. What is effective voltage then? You know, you're not going to be in the top the whole time. You can go up and down, but the top is not going to be, it's going to be half the time. So half the time you are going to be in the top. But this point here, you're gonna cross more than double the time you go to 90. And this point here is considered to be the effective voltage. Is when you get the average between the top and the zero. If I look at this part here, this is here is the location over here. What degree that could be? If this is 90 and this is 0, what would that be? Give you a second. It is 45 degree. If you go and plug in sine, because my function here is a sine function, sine 45 degrees, that equals 0.707. So this is my sine. So anything on this function in this line is represented by sine. So sine 90 is 1. Sine 0 is 0. Sine 180 is 0. Sine 45 is 0.707. Voila. It makes sense, right? I hope so. If not, go back and watch this again. So basically we are representing something going in a circle into a sine wave. And that's, my friends, is the effective voltage. And the peak is at the top. We covered that already. Phase. What is a phase? So a phase is basically a current. So it's the number of currents alternating at different time intervals. So we can produce more within one current in a voltage. That sounds really like amazing. Let's look at it. So I have a picture to represent that. So alternator alternate between currents, so it produces alternating current. And it's set up of stator and rotor. If you look at your car alternator, it's basically a motor that you turn the motor and you get current, alternating current. So same as in, and looking at the phases again are the number of the current in one circuit. Single phase, one current. Three phase, three current. Is there two phase? No, there is no two phase. There's only one or three. Why? You will see visually why is that not the case. Them here, 1, 2, and 3, one after the other. This one will hit first, then this one first, the second, and then this one. This is what happens, one after the other. So you have three phases, three currents riding on the same line. Power. Let's talk about power. So we talked about Ohm's law, we talked about the power law, also known as Boyle's law. It's calculated by a voltmeter and meter. Simple as that. So that will give you the apparent wattage. So if you go to an equipment and you know what is the voltage supplied to that equipment and you have the amperage drawn out of it and you did the power law, which you got voltage over amperage, that will be what's called the apparent wattage, the apparent power. The power factor is something, it's the ratio between the true power and the apparent power. So the apparent power is what you actually calculate from here. The true power is when you go and measure the power actually being consumed, which is very difficult unless you have a tool that will measure the power coming to you. And that's what they call the power factor. So you might have an equipment, you think you have the power completely, but there is a power factor given by the power company that it's different than what you actually see and what you get. Why do we need to do that? To know that, it's because you might have an issue with the power you require from the power company, that you just got the power from here and you don't know what is the power factor. You have to ask for the power factor, so you can multiply this number by the power factor to get the true power that you actually need, which, if you have guessed, is going to be less than the power you will get. Moving on. This is my true power and this is my power factor. Okay, and if you look here, this is my cosine 45 and this is my 0.707, which is my power factor for the apparent power, or the true power that you get. So there's a power you calculate, there's a power actually you get, and this is the power factor that you get. Because again, if you think about it, if this is my wave up and down, and this is my real power here that I measure, which is 120, I'm not getting 120, I'm getting something in here. So that's what the power you see, and this is the power actually you are getting at this part. Okay, these are a few things that you might need to remember, and you can refer to them when you need to. I will pause now and post the second video.